Morning, everyone. Was your weekend? Relaxing? Great. A few things that I wanted to share with you that first of all I published another lab that on all of the previous lectures related to all of the MATLAB code that we wrote in some of the lectures to play with that code, to write additional code, to implement some things that we discussed previously, power method and other things of that kind. Let me know if you have any questions about assignments, labs, lectures. Do you have any questions about previous lectures? All right, so the plan for today is to talk about overdetermined and underdetermined systems, and this will be one of the last topics related directly to linear algebra, and we will jump next week to calculus a little bit, numerical calculus. And we will have guest lecture on the topic. It still will relate to linear algebra. No matter what you do in numerical analysis, it still relates to linear algebra, even if you are talking about calculus. So we'll convert all of the derivatives into particular differences, and differences will be written as multiplication by some vectors and matrices. So you cannot really get rid of algebra here if you do any kind of numerical calculations. So, but this will be kind of separate topic to prepare you a little bit to understand better optimization methods and other important things in numerical methods. All right, but today we will talk about, we'll get a little bit back to solving systems of linear equations. And typically all of the linear algebra courses are allocated for solving square matrices inversions, which means you're just solving a system of equations with n variables and n equations, and you're finding n roots. And as we mentioned before, you could have three types of results. One, with a single possible solution, which is unique solution to a system of n equations and n variables. Second one, you don't have any solutions. It means you have some contradictory, self-contradicting equations inside of that system somehow, okay? And third variant, when you have infinite number of solutions, where you have practically more variables than degrees of freedom. No, the other way around. So you have more degrees of freedom than you need to find variables. This means that you have infinite number of solutions to your system. So multiple equations might be proportional, or a combination of other equations. This is a case where you have infinite number of solutions. And we've seen many of that type of systems when we solve that for eigenvalues. So when you're solving for eigenvalues and you're solving finding eigenvectors, you always have system where you have some sort of linear dependence between columns or rows, the matrices in the system, because you have infinite number of solutions for eigenvalue and eigenvector problem for given eigenvalue. All right. So we saw that type of systems before, but now after we learned SVD, we can talk a little bit more. What do you do if this is not the case? This is not square system and not n variables anymore. Okay. Can we still do something like that? Theoretically, it still will be infinite number of solutions or no solutions at all. But we want to find maybe some sort of approximation to solutions, which will be close enough in terms of least squares or error or something of that kind, okay? So you'll want to minimize some criteria and to make some solution to that type of system of equations, which might not have any solutions or might have infinite number of solutions. This is the overall idea of that lecture. Like, what do we do with that type of systems? And these systems are the most practical because typically when you're doing some sort of measurements on whatever sensor or sensors, okay, and you record the data, you have always tolerances, imprecisions, noise, and all those things. So when you record these numbers, they are not correct numbers, okay? So sometimes the system might not even have any solutions, and you still need some solution which is close enough. This is the overall idea of this topic, okay? The first claim is that not all matrices are invertible. If you have a rectangular matrix, it's not even defined how you invert the matrix. All right, and we want somehow to generalize invertibility of matrices for non-square matrices and non-singular matrices, where you actually cannot do that officially by finding all of these determinants and other computations that we did before for square matrices where they are invertible. So this is called pseudo-inverse, or Moore-Penrose pseudo-inverse. Okay, this is what we'll be talking about today. We'll start talking about that. And this allows you to kind of invert relations in terms of least squares, which means it will invert the matrix, assuming that you still will have some error, but this error will be minimal out of all possible errors that you could get by inverting that matrix, okay? So you have two different type of cases, as I mentioned. First case is where you have infinite number of solutions. And then you want to find solution of AX equals B. A is matrix, B is vector, X is vector that you want to find. So we will find such as, and you have infinite number of solutions here. So you will find solution which provides minimal X norm. So second norm of X will be minimized by a particular solution, which is a pseudo inverse that we'll be talking about. Which means out of all possible X's that solve the system of equations, which is underdetermined, we'll call that underdetermined, so you have infinite number of solutions. You will have one which is in a sense optimal solution. And this optimal solution is minimal X. Like all of the elements of X will be as small as you can get them. Magnitude will be smallest for each element of X out of all possible X's which solve the system. All right? So this is the first idea that we want to describe. And second idea, when you do not have any solutions, which means your signal is noisy, your measurements are noisy, your matrix A or matrix B are not reliable, and you still want to find X, but no X satisfies all of these equations because you have some contradiction within that. You might have like very long matrix A, which means you have many equations, but only two variables, let's say. So A is, let's say, 100 by 2 matrix, which is very long, like very tall matrix, but very narrow matrix, okay? So 2 columns and 100 rows. So obviously you have 100 equations with only 2 variables. Almost surely you will have some contradictions in these equations, which means they will not say the same thing. And pay attention that even for that kind of system, I can find cases where even for the tall matrix, I have no solutions or infinitely many solutions, right? So it's also possible. And for the first case, it's also possible not to have any solutions and not infinite number of solutions. So I can figure out some matrices which are kind of weird, but they are of that kind, okay? So it's not necessarily that all of the tall matrices will have no solutions, and not necessarily all of the wide matrices will have infinite number of solutions. I can find cases where it's not exactly true, but typically this is the case, okay? This is very typical case. If you pick 100 equations, most likely they will contradict each other. They will not be the same equation, okay? They will not give you the same answer, and definitely not infinite number of answers. All right? Is it clear what I'm saying? So I'm talking about typical case. Yes.
Question is, if there are infinite number of solutions, how confident are we that minimum of the X is the right solution?
We are not confident at all. We are assuming that this is what we want. Okay? So you want smallest X out of all possible X's, and if you want to optimize on something else, on some other criteria, then you have other solutions. There's a problem, okay? Again, you have infinite number of solutions, and problem of optimization in general is to find a solution which is optimizing particular criterion, right? And this criterion you define like what you want from that X to B. You are defining particular criteria that says like X needs to be such and such. So this is only one possible criteria for minimizing X. And if you want it, fine, great. You found analytical solution, and this analytical solution will be that pseudo inverse, okay, for that particular optimization problem, okay? If you want maximal X out of all possible X's, if it exists, okay, then it's completely different solution. If you want that X to be as close to 1 as possible, like norm 1, then it's completely different solution, but it will not be that Moore-Penrose solution. right? So it will be something else. So for that particular problem, this is the solution. Yes.
So we're trying to find the best approximation of X.
Yes. We want best approximation of X, which is smallest one in terms of that norm. And this will tell you that most likely the vector will be pretty sparse. You maybe will have some zeros here and there. So it's nicely behaving vector. Many times you want actual sparse vector where you have a lot of zeros in the vector. Many times this is what you're looking for. And then you need to minimize norm 1, not norm 2. So L1 norm. So when you're minimizing L1 norm, this making the matrices or vectors sparse. You have a lot of zeros. And this is what you do typically in like sparse sampling type of mechanisms. This is what you optimize on, right? So these are the problems that we are trying to solve. So I showed you, first of all, like, what is the solution, and I haven't showed what that solution is in terms of formula and how you compute that solution. I just named it so far. So we need to define what is overdetermined and underdetermined, and then I will show how it actually works. All right. So if system is invertible, I'm just showing here shapes of the matrices and vectors. Then you have unique solution, and the solution will be A inverse times B. To the system AX equals B. So this is a solution that all linear algebra courses are devoted to, or most of the linear algebra courses devoted to, how you compute that kind of thing. Okay, with Gauss elimination and other techniques, okay? So you have square matrix here, invertible, vector of the same size, and output is also vector of the same size. Okay, they all n by n, n by 1, and n by 1. Okay. Now, underdetermined system means that your matrix is wide, thick, whatever you call it. Okay. So m, which is number of rows, is smaller than number of columns in that case. So your x vectors that will be possible to multiply is that x vector should be long, tall, right? And your output will be as short as your original matrix, which is m by 1. Okay, so this will be n by 1 vector, and this will be m by 1 vector for matrices m by n. And this matrix is clearly not square, so you cannot invert it really. And we are trying to find that smallest x in terms of norms that I just defined. Since you have infinite number of options here, typically, again, it's typical, not always. Typically, you have infinite number of solutions. Overdetermined system is when the matrix A is tall and narrow. So you have m larger than n. So this vector is short now, and this vector is long now. All right. So you have small number of variables, which means degrees of freedom practically. If you have small number of degrees of freedom, it's very likely that you will not have any solutions because you have too many equations that probably will contradict each other. All right. And we want to find solution to that set of parameters, x, which are variables in that x, which produce minimal error from that vector, which means if you're thinking about that equation as matrix times that vector that you found equals some vector plus some error, okay, some vector of errors. So you'll have some vector, additional vector of n by 1 of errors. This vector will be smallest in terms of norm. Okay, so you're adding minimal error to each one of the rows in terms of least squares. So sum of squared errors will be minimal. This is the overall idea in terms of least squares. This is what least squares are. All right. Any questions on that? So far I'm describing just the problems that we are going to solve now. Is it clear what are two problems that we are dealing here with? All right. So here is the solution. So we learned about SVD, where you can write matrix as SVD inverse. So for invertible matrix A, where A is square and invertible, it's very easy because you can say, well, I have sigma decomposition here, which is SVD. So you have U times sigma times V transpose, as we've seen before. Inverse of that thing, you inverse the order of matrices, if you remember when you're doing inverse of multiplication. So you get V transpose inverse, sigma inverse, U inverse. All right. Now, U transpose inverse, since U is orthogonal,
transpose is inverse. So inverse will give you V back, right? So it will be V. Sigma inverse will stay as is, but this is diagonal matrix, which means it's just all elements, diagonal elements inverse, right? This is what that thing is. So this is still diagonal matrix where you're inverting all of the singular values on the main diagonal. And then same thing, U transpose is U inverse because it's also orthogonal matrix, okay, or unitary matrix. So you get U transpose here. This is very simple computation for inverse of A when you have regular SVD decomposition of matrix A, okay? All you do, you just switch in the order of these matrices and you switch in the transpose on these matrices. That's it, you just multiply them in different order. This is how it works, right? But this for invertible matrices. It's not very interesting. All of these matrices are square and invertible, so it's not a big deal really to do that. And you would do the same thing with eigenvalue decomposition. You could do the same thing, okay? You would get the same values for all eigenvalues, you inverting eigenvalues and so on. So what happens if the matrix is not, if not square matrix, it's some sort of rectangular matrix, and that matrix is not invertible anymore. So it's not even square matrix anymore, obviously not invertible. And you have some sigmas which are zeros, right? So you have some sigmas which are going on the main diagonal, and then you have like a bunch of zeros in all kinds of places. You clearly cannot invert it because any row or column of zeros gives that makes that matrix not invertible. So what you can do, you can invert whatever you can invert and keep zeros as they are. This is exactly what pseudo inverse is doing. And since all of the columns are organized in terms of importance, these later ones will not be really important that you haven't inverted them, right? Just forget about them. You will just ignore them completely. So what happens is, let's say you have that kind of matrix, okay? This is your sigma matrix. So you have 2, 10, and then last one is 0, so it's clearly not invertible. Okay, you have column of zeros. Now, pseudo inverse, which we also use in that dagger symbol, sometimes it's, some textbooks are using plus symbol for pseudo inverse, okay? So pseudo inverse is 1/2 and 1/10 and 0 here, okay? And keeping all of the other zeros. So you're inverting whatever you can invert, and you keep everything else as is. And then that Penrose pseudo inverse will be just V times, like, follows that formula. You're inverting whatever you can invert, so it's pseudo inverse of sigma, and you transpose. All right, so this is the overall idea where we are going with that. And if we are already in thin or compact form, and I said that these are practically equivalent, just the original matrix decomposition, like singular value decomposition of the matrix A, if you remember. There you have square matrix sigma with non-zero values because we already remove all of these columns, which in the multiplication will just disappear. So we don't care about them. So in that case, you actually can invert that matrix. All right, and you can write it exactly like this one. So for both invertible and non-invertible matrix, pseudo inverse will be just that same in compact form or thin form. Any questions on that? And we will develop like what that means in terms of matrices A later, but this is how you do that using SVD. This is pseudo inverse. This is how it is defined. And I'm not proving right now like why it is like minimally squares or anything like that. We will see that later. Why this solves the optimization problems that we just discussed. But this is the proposed solution. Is it clear so far? Okay. So here's additional solution to the problems that we have. So optimal solution, which is that thing, will be pseudo inverse, which is what we discussed so far. So if you have system which is AX equals to B, and you want to find X, which is optimal in the sense that we just discussed, this will be the solution, okay, for both problems, all right? So additional thing is this is what we want to prove, that you actually can compute pseudo inverse using that formula, which is very nice for M larger than N and equals to rank of the system, okay? So if rank equals to the smallest, like if this is like tall and narrow matrix, and you have rank which is all of the number of columns that you have, then this is the formula that you have to compute. For the other case where n is larger than m, this is the formula that you need to compute, okay, to minimize the norm of vector x. So this is least square formula, and this is minimum norm type of formula for that kind of thing. Okay, and we will derive that first formula first to see where this formula is coming from. But frankly speaking, you saw that formula before, twice. Probably haven't noticed that, but you saw that before. This is practically projection, orthogonal projection into particular subspace formula, where we've seen that in some of the examples, that same formula, where you just projecting vectors in orthogonally onto particular subspace, you get that exact formula from there. And we derive that one way. Now I will derive it completely different way. Okay, and then I will derive it third way, just to show that all of them are practically equivalent to SVD. So first thing that I want to show right now in the derivation is that practically speaking, that formula is equivalent to what I described in SVD form of pseudo-inverse. All right, so that pseudo-inverse that I just defined at the top here, which is V sigma dagger U transpose, is the same thing as A transpose A inverse A transpose. Okay, this is what I want to show, that they are completely equivalent things if M is larger than N. And you have that kind of derivation. Any questions on that? Okay, so this is what we're going to do right now. All right, so here's what we have. So you have matrix A, which is defined as U sigma and then V transpose. You have A transpose, which is defined as V sigma U transpose. Okay. And we assume that we have a compact economic form, one of the forms where this thing is invertible square. Okay. Other things we don't really care about that much. So here's what was proposed for that kind of form. This was a formula that I want to show that they're equivalent. So it's A transpose A inverse A transpose. Okay, now I'll just put all these formulas inside of these things, replacing A with these formulas. So it will be A transpose, which is that thing, V sigma U transpose times A, which is that thing, U sigma V. Now it's inverse. Okay, and A transpose, which is V sigma U transpose. Okay, so far, so this thing is cancelled because this is orthogonal matrix, it's I. Multiplication by I will not change that thing. This thing multiplied by this thing is just sigma squared. Okay. So these are diagonal matrices. If you multiply diagonal matrices, it's just multiplication element by element. It will give you each element squared. So a singular value is squared on the main diagonal in that matrix, kind of eigenvalues, symmetrical matrices at least. All right. Now we need to do inverse. So to do inverse, we need to invert the order of all of the things. So it will be, okay, so we are doing inverse of that thing. We will get E, which should be E. So this will be U sigma V transpose, yes. So V transpose inverse. Then you have sigma minus squared, which is all of the elements 1 divided by that element squared, diagonal matrix. And then V inverse times V times sigma times V transpose. But as you know, V inverse and V transpose the same thing. So that thing gets lost in the computation, okay, cancelled. All right, now you have sigma inverse 2 times sigma. So this sigma disappears, this 2 disappears, becomes 1. Right? This one, it's like inverse, it will be V. So what you get from here is V, sigma inverse, and false. And this is exactly the definitions that we had before. Singular values. All right? So these two things are completely equivalent. So this formula is exactly that formula. They are equivalent in that sense. Okay? Any questions? Yes.
Wondering why A silver equals to A transpose A inverse and then
This one?
this one. Yeah.
This one? So this is how we define that this, what I wanted to prove is that this thing equals to that thing. So I define this is pseudo inverse. And this is pseudo inverse given, so I gave you two forms of pseudo inverse for the same thing, okay? One form was that form which we developed using SVD, okay? And then I said, let me prove that's also equivalent to that. So this is proof that this thing is equivalent to that thing, which means instead of that computation where you're doing SVD, you can compute it directly using that formula for matrix A. It's more convenient, right? You don't need to do SVD anymore. All you do, you compute that formula instead. Don't do SVD, okay? This is your least square solution for the problem. So practically speaking, this is what I wanted to prove. That this thing equals A transpose A inverse A transpose. Formula. Prove that formula. So the inverse. Now, it's difficult to remember that kind of form. Do you know what is the easiest way to remember and develop that each time you need any kind of least square? Because this formula is used in like billion applications, okay? This is the most popular formula. This is least squares. Like everything you can convert, everything in optimization you can convert into least square problems. And least square problems are like all over the place. So you need to use that formula all the time. And everything you will have is all kind of modifications on that formula. Adding here W and here W for weighted least squares. And then you will have like plus some I times some lambda for total least squares. And then you'll have all kind of things, okay? But this is basis for all of it. This is a formula, okay? Like how to remember that formula without like going each time to textbook or to lecture. So here's how you do that. You have system which is AX equals B. All right, this is a system that you want to solve. So what you do, you multiply both sides by A transpose. This is not changing the system, but this makes that thing potentially invertible. Okay? Because you can multiply by any matrix from left and right, it's not changing anything, okay? But this makes that thing invertible. Hopefully, we will see what happens if it is not, okay? This is not always true. But in most cases, typically this is invertible, all right? Now, how do you solve that system of matrix equations? You want to get rid of that part. Or how you get rid of that part? You multiply it by inverse of that thing, both sides. And then you get that formula. So if you multiply it, this thing will cancel. On that side, you will have A transpose A inverse, A transpose and B. That's it. Here you will have X left. This is formula for these squares, okay? So all you need to remember, multiply from left by A transpose to get to make that invertible, and then get rid of that entire thing, which is invertible, by inverting it. That's it. This is a derivation that you need to remember. So this is very simple to get to that formula, even if you don't remember it at all. Okay, how all of that stuff. Because clearly you will not go from that thing through all of these derivations, adding some variables. It's like too much. It's impossible to remember it. But this one is relatively easy, okay? It's like one step type of derivation. Any questions on that? All right, so I'm not sure if you need to learn that thing, how to do all kind of computations with these matrices. This is just interesting property of the pseudo inverse and how you work with that. And I put it here because I thought that maybe I will include in homework something similar to that for you to develop, that you will see just one example how you simplify things. But this is very similar to that kind of thing. You just substitute all of the A's with the SVD, and then all kind of things in the middle cancel, like V transpose V or U transpose U, and then it all cancels out, and then you get something very simple like that. Okay, so this is how you manipulate all of this SVD decompositions in general. All right. So, how many of you seen before linear regression? Okay, so at least half of the class seen linear regression before. And this is as simple as just fitting linear line, like straight line, to bunch of points. And I will show that this is also least square solution in a sense. We can convert it into least square solution in a very simple way. And regression problems, all regression problems are practically least square solutions to problem when you minimize in sum of square errors from the particular models that you have. So you have some model which could be particular line function of some kind, and you are trying to fit that function, whatever it is, analytical function, to a bunch of points. So in that case, I have here multiple green points. These are data points. And as you can see, they are kind of noisy. They're in all kind of places. All right. So these are my data points. And I want to pass straight line for correlation purposes or whatever other purposes, just to see like what is the best fit line to these points. This is my model. My model is alpha x plus beta. Okay, so this will be y-axis, this will be x-axis. And I'm sorry that I'm using x here for a completely different purpose, not as a vector x, it's just coordinates x and y of points. Okay, so you need to get used to change of notation on the fly. So what happens is, let's say this is my optimal line that I'm looking for. So for that line, I need slope and intercept, right, to define that particular model. So it will be alpha and beta in that case. So what happens is I want to minimize all of the errors which are EN errors. And this is vertical errors from that green point to my model. So I want such a line for which sum of the squared errors, EN1, like E1 squared plus E2 squared plus E3 squared, until you get to the last point. So sum of the squares will be minimal. This is the point, entire point of regression, right? So you're looking for such a red line, which will minimize all of these distances. That distance plus that distance squared plus that distance squared plus that distance squared. You have all of these distances from the line, okay? You want to minimize sum of all of the squared distances. Y squared? Any idea why squared and not just distances? Sum of the distances?
Some will be positive and negative.
Yeah, so why not sum of absolute differences?
And if some negative and then positive.
So absolute differences are always positive. There's absolute value between, let's say, this one is negative, right? So subtracting that point minus that point, absolute value will be that distance. So summing all of these distances and minimizing that one. Why not that distance? Why square distances? Why you want to add squares of distances, not absolute values of differences? And in all regression problems, you will have least squares. Why not least absolute values? Because absolute values are also positive, right? They are also contributing the same thing to errors. But people use practically exclusively squared errors, not errors. Y squared. So this is a very tricky calculus question. Any idea? Because I'm sure you probably heard, like most likely heard before, least squares name at least, right? People using least squares everywhere. Solution is least squares. Okay, like you want random problem, solution, least squares. Okay, they throw least squares at everything, every single optimization problem. Why squares, not absolute values? Absolute values are easy, right? You're just subtracting one number minus another number, making absolute value of that, done. You don't need to square anything. You don't need to multiply one by another one. Like less computations. Just ignore the minus sign if you get it. Subtract one minus another, ignore the minus sign. This is what absolute value is.
Because after square, you do the square root. So
No, this is for Euclidean distance. We are not doing Euclidean distance. We are minimizing sum of squares. We are not even doing root of that. Like root will not change anything practically, right? Root will just, it's monotonic function, which is not changing the order of error. You can do like minimizing RMSE, root mean square. You have that kind of minimization as well, but you don't have to. You can minimize just squares, least squares. Just saving one operation. No?
square method could be like, you were not affected by an outlier.
Yeah, root mean squares definitely have their own advantages, okay? But this is not still not absolute values. They are still square root of sum of squares. Why squares? Why not sum of absolute values? Without root, then you will have also same thing for outliers, same advantage. Why not to use that advantageous approach? Sum of absolute values instead of square root of sum of squares. Makes more sense, right?
Because we can differentiate the squares easier?
This is a problem. The absolute value function, which looks like that, it's not differentiable at zero. It has a breaking point at origin, which you cannot differentiate. And to find maxima or minima of any function, you need to compute derivative, which is Fermat theorem, which says that derivative should be zero at any maxima or minima, any extrema point, practically, right? Absolute value, you cannot find derivative for absolute value, okay? Because it has no derivative at zero. It has two different derivatives. It's like one directional derivative only when limit comes to the 0 point. And this is exactly where you want to optimize it, where it's like close to zero. So you will have problems jumping from one to another. It will not converge. It's mechanical problem, a computational problem, numerical problem that you cannot really compute with absolute values much, because you cannot find derivative analytically of the function. It does not exist at zero. And this is why people do square, and square is easy to find derivative because this is polynomial, right? And polynomials, we know that derivative will be twice whatever that thing is. This is a derivative, okay? And it's linear in that sense. It's just multiplication by 2. Very easy to compute and very simple. That's why people using these squares. Squares are just much easier for computational purposes and numerically stable and not like absolute values. But people still do absolute values, sum of absolute values, minimizing that. Again, it's like L1 minimization. It's significantly complicated algorithm, how to make it work and how to make it converge. And what you do to make it converge is like separate big issue, how you converge that kind of thing numerically. But it's possible, people are doing that, but this one has analytical solution. Minimizing sum of absolute values has no analytical solution, no formula that you can use, okay? So this is a complication here. You cannot compute formula for that because you have no derivative for that, all right? Okay, so what we are doing here, we are trying to represent linear regression as minimization problem, where we are minimizing all of this kind of differences from the model, okay? So you have that model, which is straight line, and then you have all of that sum of different square differences that you are computing, and you want to minimize it. So how do you minimize it, okay? So let me show you a few things that maybe you'll find this all in the future as well. So it will be kind of introduction to next lecture calculus as well, with linear algebra in a sense. I want to give you 2 proposals how to compute derivatives of matrices in general. vectors matrices. Practically derivative of vector is just derivative of each element, so it's relatively simple. But for matrices, you need to know two formulas, okay? I have formulas which is dx transpose A to dx, which is first formula. This will be A transpose. Okay, this is derivative of kind of AX, but transposed version. So if you think about it, it's like A transpose X, and all of that transpose, and derivative on that. And second formula is dx transpose AX. We will call it later quadratic form. It's additional A, X transpose A transpose A. But for square form, X will be twice A transpose A X. So it's something similar to like AX squared kind of thing. Okay, but X is multiplied on the left and on the right. It's transpose. So this matrix, it doesn't matter what kind of matrix is that. I'm writing that because we don't need that specific matrix, but it could be any a theta matrix. Okay, some matrix, whatever it is. All right, so these are two formulas that you need to know. Okay, and now what we are looking for is to minimize that norm. Well, these are the errors, right? So our system was AX equals B plus some error. So AX minus B is that error. And you want to minimize, let's see. This is the entire point of least squares. So what I'm trying to derive here is again, same formula that we saw before, but using completely different thinking mechanism. Right, so here now I'm thinking about it as minimization process or optimization process, okay? I'm optimizing or minimizing that thing. This is my criteria. I want smallest possible error between this one and this one, right? Given some system of linear equations which is overdetermined. So you don't have any actual solution. You cannot invert A in that case. But I want to find that kind of minimum. And this minimum will be on all of the x's Rn. So I'm searching all of the n-dimensional vectors, whatever they are, substituting them here for given matrices A and vector B, such that this number, and this norm is a number, okay? So this is practically vector, right? Do you understand why this one is a vector? This is this vector and this vector's difference of two vectors is vector. So it's regular vector. You're making all of the values squared because this is square here, and this Euclidean norm. So it's sum of squares, sum of squared errors, okay? And then you're minimizing on that thing. This is what you're looking for. So it will be minimum, and I'm substituting on all of the x's, substituting ax minus b transpose times ax minus b. Remember, this is what norm is, dot product between vector and itself. Right? So let's open the parentheses and see what happens. That's ax transpose will be x transpose A times AX. Okay, this is first element times first element. All right, I'm doing Z transpose minus Z transpose. Let me write it. This will be A X transpose A transpose minus B transpose. Okay, this is that thing together with transposes. Okay, so I'm multiplying that thing by that thing. It's X transpose A transpose times AX, okay? Minus B transpose times AX. This is this one by this one. Now I have this one by this one, so it will be plus X transpose A transpose B. Okay. And minus B transpose B. This is what we have here. Okay, now I need derivative of that same. Call it. What letter do you want to use? Function. So you want df to dx to be 0. Means you want extrema point, Fermat theorem. The derivative should be 0. Function of x. So I'm looking for x, for which the derivative will be 0. So what is that derivative of that thing? So I'm using that formula first for that element, because this is function of x, that kind of function of x. So it will be twice A transpose A x. The derivative. Okay, in matrices. Now pay attention what that thing is, and what that thing is. They are practically the same, so you have supposed to be not plus but minus here. Transpose with minus ax and ax minus b. It should be minus here. Okay. So instead of this thing, you can say that this is practically twice that thing. Okay. Now, twice that thing, you're using that derivative of x transpose times something. Okay. You will get plus 2a transpose b, but this is minus b, so this will be minus here. Minus twice a transpose b. And think about b as constant, right? So it's like, and 2 is constant. So you can, derivatives, you can multiply by constant. Every time you multiply by some sort of constant, it stays as is. Okay, you're not changing anything in the derivatives. All right. So what is that saying? So it's twice a transpose times ax minus b. Recognize the equation. You can cancel 2 if you want. With 0, it doesn't matter. Recognize that equation, result 2. This is the equation. This is the equation. Called normal equation. This is exactly the way I told you, like, to remember how you compute the inverse of that matrix. How do you solve that equation? You just get rid of that thing. When you move that one to that side, so this will be, instead of that thing, we'll have equal here. Then you multiply by inverse of that thing, both sides, you get regular formula, which is x equals a transpose a inverse a transpose b. This is least square solution of the problem. Same formula. So we developed that 3 different ways. There's orthogonal projection, we got that formula, we got that same formula from SVD, and now we've got that from minimization of some error for linear regression, okay? We have the same thing for other regressions as well, but this is 3 different ways to look at that same problem. That's a universal problem. Any questions on that? Talked? Yes.
Y partial f partial x equals to 0.
Why what? Equals to
Partial x, partial f, partial x equals to 0.
Where do you see it?
Means the derivative f.
Partial derivative of f to, why is this one equals to 0? You are looking for minimum. How do you find minimum of some function? So you're looking for minimum of that function, as this function is a function of x. So this is f of x. Okay. Right. Okay. F of x. So you're looking for that type of thing. How do you find minimum of that function? Sure. That f of x. How do you do that? Any function. Like think about one-dimensional function. Like let's say x is just variable. How do you find minimum of, like in calculus, how do you find minimum of any function? Let's say you have function x squared. Okay, so f of x equals x squared. How do you find minimum? The answer is 0, but how do you find that 0?
2x to the power.
You do df to dx equals 0. Means 2x equals 0, x equals 0. Let's say you want, I don't know, let's shift it to some other place. You have x plus 5 squared. It's the same thing. So it will be, instead of that thing, it will be twice x plus 5. Okay. And then 0 will be at negative 5. X equals to 0. Derivative equals to 0. X equals negative 5. That's how you compute minima for any kind of functions. Okay. Same thing here. We are saying, and intuitively, like look at that intuitively. Like what does it mean that you have 0 derivative? Derivative is slope, right? So if you're thinking about slope, which is 0, it's horizontal line, which means at a particular point when you touch in some function at a particular point, so your derivatives are positive or they're negative, right? But where you have maxima or minimum points, where derivative is switching from positive to negative or the other way around, okay? From negative to positive. And this is exactly where derivative is 0. It's moving from here until you get the peak, and then the peak is flat, right? Horizontal, which means 0 slope, okay? And derivative is slope. And then when you're touching here, this is exactly the condition for extrema points. So it could be, I don't know if it is maximum or minimum. So I don't know if what I thought here may be maximum. And it's very unlikely because this x could be as big as you want. Technically speaking, it's unlimited. In a sense, you can have like infinite size here. All right. So it's most likely to be minimum and not maximum. Okay. Again, this assumption it needs to be proven, but believe me, this is minimum, okay, for that course. So you minimizing that function, and that function will be df to dx equals to 0. This will be the critical points where you suspect you will have some sort of minima or maxima. And in that case, you have only one solution for that thing, right? And if you have only one solution, this is the minima. You don't have others. So it's, you know that this is what it is. Okay? Any other questions? Okay. All right, so we derived that for, let me check again. All right, so you're just using regular least square solution, which is you putting all of these numbers into the matrix and you get solutions of all kind. And this matrix will be actually very simple. This matrix will be very similar to this one, but before we go there, I want to give you more generic solution for any kind of polynomial and regression, which could be quadratic, cubic, whatever. And practically it could be actually any function. It doesn't matter. As far as this function is combined with a parameter times some function plus another parameter times another function times third parameter, then you have linear combination of functions, okay? When your representation, analytical representation, is just linear combination of functions. And in that case, you're just using simple basic basis for polynomial functions, which is 1, x, x squared, x cubed, x4 power, and so on. Okay, this is most basic type of function, polynomial function, okay? But you can replace that basis with any other basis, okay? It still will work the same way. So the assumption will be that your function is something like that. You will have y equals alpha plus beta x plus gamma x squared plus whatever. You just decide how many of them you want, how many variables you want. So what happens is if you write that in the matrix form, here's what will happen. Let's say you have a bunch of points, and each point is like x1, y1, x2, y2. Each one of them will have like arrow 1, 2, 3, and so on until you get to the last point, and you have n points. Okay, so the last one will be xn, yn. This is coordinates of the last point. So what happens is take each point, okay, and for each one of them, you can write that y1 equals alpha plus beta x1 plus gamma x1 squared plus and so on, right? So if you think about that, this is linear combination because each one of these numbers, each one of these like x's is a number. In that case, it doesn't matter if it is square of the number, cube of the number, it's still number, some number, whatever it is. So you have alpha times 1 plus beta times number plus gamma times number plus delta times number and so on. So you can write that thing as that system of equations for each one of these dots. So first dot will be y1 equals 1 times alpha plus x1 times beta plus x1 squared times gamma and so on. Second point will be y2 equals 1 times alpha plus x2 times beta and so on, all right? So what happens is that all of that matrix becomes matrix of numbers because these are just coordinates of your points. This is also vector of numbers, which are y coordinates of your points, just numerical values, right? And you have vector of numerical values equals some matrix of numerical values times some unknown set of parameters. Now we know how to solve it, regardless of how many parameters you have. Like previously, we could solve it only if you have n parameters and also n by n matrix here. Then you could solve it, and equations and n variables. But now we can solve it for any number of variables, and then we will say, well, they do not really have to fit all of that parabola, for example, right? They could be kind of noisy. It doesn't matter. Yes, we will not have one single invertible matrix here because they will not fit exact model. Okay, you don't have solutions here really. But you can provide solution in terms of least squares, which means minimizing the total error, vertical error squared from all of these points. This is the overall idea. So we will call that vector b because we want some a times x equals to b, but sometimes I will call it y maybe, I'm not sure. Let's see. And this matrix is called van der Monde matrix by that name of Alexander Theophil van der Monde, who invented that long time ago, long before linear algebra, okay? And he worked on determinants and other things, but no linear algebra at the time. Linear algebra was invented probably second half of 19th century, like more than like about 100 years later, all right? But he was one of the pioneers of the ideas of using determinants and matrices, okay? So this is kind of, he probably haven't wrote it as matrix at all. But the idea was that you can write that as linear combination of different parameters. And this could be any kind of functions. It could be like f1, f2, and f3, 4, whatever. Okay, any analytical function. So we'll call that V, just to honor his name, van der Monde matrix. And this is n by n matrix, or could be some other types of matrices. Okay, and each element in that matrix is just xi to the power of j. All right, so each element you can write that way. And I don't know why it's so high here, but the solution will be just regular with, let me just correct it here. Okay, solution will be just regular formula instead of A I'm putting V, but it doesn't matter. That vector of parameters that you want to find, which are coefficients of that polynomial, will be just V transpose V inverse times V transpose times vector B of all of the Y values. That's it. So the entire point of least squares is to write everything as a AX equals B of some kind. And then you're solving that with least squares. And A could be not rectangular, not square, it could be rectangular. some kind, okay? This is the overall idea. So we will see multiple different applications where you actually can write that as AX equals B of some kind. Yes, question?
My question is for the linear regression, for the polynomial fitting.
Yeah, you'll have only two first columns.
No, so my question is for the function which you have to minimize so that you get the minimum difference between AX and then B, would it always be a simple quadratic equation such that if you find a minimum, it is kind of the...
No, you're not looking for the degree. You decide what your model is first. So first you decide, I want, for example, a quadratic approximation to that bunch of points. Like in that case, it looks like a parabola to me, I don't know. If you decide that this looks like a parabola to you, you're saying, I cut it here, I'm not using that plus here anymore, okay? So I will have first three columns. So it will be n by 3 matrix. And I will use that formula to compute my quadratic model fitting this particular green points, all right? If you decide that I want only first order, let's say I want linear regression. So how I solve linear regression? And you'll have like statisticians that are using completely different formulas with sigmas and other things, but this is exactly the same thing. If you actually compute explicitly all of the parameters in your sigmas, you will get V transpose V inverse times V transpose times B. Same thing, it's just much simpler writing, I would say. So in linear regression, using that column of ones and that columns of x's, you have only two columns. So this matrix will be n by 2. And then you put that matrix here and you get your linear regression, which is solution to the previous problem, to that problem.
I think my question is, so what if there are multiple minima?
What if you have multiple minima and maximums, and you have much higher order polynomial to approximate it, okay? And you decide first on the order of the polynomial, and this matrix will be much wider than, you'll have many more parameters to approximate. You still will have probably more points than parameters, and you need always to have more points than parameters that you want to estimate. Otherwise, you will not have enough equations. Otherwise, you will have infinite number of solutions. And again, out of all of the solutions, if you still use the same formula, you will get the one which has minimal vector of all these parameters. So if you have infinite number of solutions here, all you will get with pseudo-inverse is the one which is having the minimal norm. This will be the solutions that you get out of infinite number of possible solutions if you don't have enough equations, okay, not enough points. And would that make sense to fit like higher order polynomial if you don't have enough points? It's like probably not really. Like you will not have that many minima and maxima, and you don't want to fit to every single point because you have some noise, right? So this is how it works. Okay, any questions?
All right, just to remind you that previous time we talked about overdetermined and underdetermined systems related to least squares and solutions of least squares. And today we'll be continuing talking about least squares and their applications. And you have plenty of them. So we'll go through whatever you will have time to go through. You can find many more applications for least squares. You will see all kind of configurations of least squares, different types of least squares. Solutions that you sometimes need for different types of problems, and what are advantages or disadvantages of each one of these approaches. So just to remind you that what we try to do is to do pseudo-inverse of matrices which are not invertible. When you have too many equations, or the number of equations is not enough to cover all of the possible variants and to have unique solution, okay? So we are talking about cases where you have not unique solution, infinite numbers of solutions or no solutions. All right, so you had regular matrix inversion and then pseudo-inverse with that type of wide matrices. And then you have a lot of variables, but you don't have enough equations. So you have a lot of degrees of freedom. So you need to choose some of the variables freely and then to compute all of the other variables based on the free variables. But in that case, you have obviously infinite number of possibilities. And we particularly picked possibility where the sum of squares of all of these variables will be minimal. Okay, so we're minimizing that kind of criteria, and this might be useful or not useful for whatever application you're using.
it gives you mainly like smaller values in the x, in the vector x, right? So your variables will be kind of small. Again, is it good or bad for your application? It depends. You might want it or you might want something else. But this is like that kind of equation, that kind of solution you get analytically. And this is a big advantage of that thing. So you don't need to iterate, you don't need to compute anything. It's all analytical formula. You just put numbers in the formula and you get the answer for that analytical optimization problem, which is, believe me, really rare. You almost never have analytical solutions for any optimization problems, linear or nonlinear. Okay, you have only a few cases where you actually can solve it as a formula. So you have actual explicit solution and not implicit solution. Okay, so this is relatively rare, and this is why I'm bringing it here. And this is more popular case where you have a lot of equations, and they are your measurements of some kind, and each row might be like single measurement, and each column will say something about linear combination of your variables in the output that you measure. So it's linear system of equations where you have more equations than variables. And in that case, where you have more equations than variables, you clearly have almost never have single solution or infinite number of solutions. You almost never have any solution, okay? Because these equations contradict each other because of noise tolerances and so on. Okay, and this is where we apply least squares, solve the system of equations. And then we learned that we can do that using SVD. And using SVD, we found that we can consider the inverse, and using the inverse, we can have some least square solutions, which are optimal for these two particular cases. And these particular cases are actually very broad, so it's like used in millions of different applications. All right, and these are the solutions. Summary of all of the solutions for different types of rank of matrices. And then we talked about linear regression to fit points to straight line or to any other kind of polynomial. And I just mentioned, but haven't showed that instead of x squared, x cubed, you can use any other function as far as your result or your measurement is linear combination of these functions. So you can use practically any kind of functions, better orthogonal functions, but technically you can use all kinds of functions and to write your function of interest that you're trying to fit. Bunch of points you're trying to fit to that bunch of functions, yes. Using these squares, same mechanism, same algorithm, same everything, just instead of x1, x2, x3, you will have some function of variables that you have, okay? And this will be just a number, practically. Why? Because this function will be measured at that particular point. But it doesn't matter if it is polynomial or not polynomial function. It could be any function. And this is why least squares approach is so broad and so generic. You can apply it to any set of functions as far as your final function is linear combination of these basis functions. Right? This is the overall idea of all of the least squares. And we said that this is called Underdetermined matrix. We had some solution for that. And now we will talk about some modification for the least square mechanism, which works better in many different cases and very popular. It's called also ridge regression or Tikhonov regularization by the name of the developer of that technique. And the idea is that A transpose A, which is used, if you remember, like if you go to the formula here, okay? So the pseudo inverse for these squares is A transpose A inverse times A transpose. This is in the table, this is the second row. Okay, where M larger than N, you get A transpose A inverse times A transpose. This is how you compute pseudo inverse. Okay, and this is your least square solution. Now, who told you that A transpose A is even invertible? Okay, in many cases it is, but not necessarily. You might have A transpose A, it is square matrix, but not invertible. Okay, it might be singular matrix. It might be very similar to singular matrix, which is close enough. So one of your eigenvalues might be really, really close to zero, not exactly zero, but very close to zero, which means that when you invert in that numerically, you get a lot of numerical errors gathered together when you invert in matrices. So your inverse result will be not accurate at all. Okay, this is what will happen numerically when you're computing that algorithmically using QR or whatever other method to invert matrices. All right. So here we have a problem. Like, what do? You cannot do even pseudo inverse now. And I said, like, well, we have that universal great method for doing all kind of cool stuff, and you can invert now even not square matrices. So we need some solution for that. Okay, so this solution will be that particular Tikhonov regularization. And when this matrix is not invertible, or very close to being not invertible, you might have infinite number of possible solutions to that kind of equation. So when we have infinite number of solutions, all we need to do, we need additional constraint on our optimization process, okay? And this constraint will be, as usual, just minimizing the norm of the solution. So it's kind of blending what you do with like too many equations and too little equations. So you blend it in the same criterion. And what we will do also, we will give it some sort of weight, okay? So this is called Tikhonov regularization, when A transpose A is not exactly invertible. And this is when it works pretty well, okay? And what we will do, we will add weight coefficient, which we will call alpha. And this will be importance to minimize X versus minimizing the least squares of the error. Okay, so it's to make least errors least square. Okay, so it's kind of compromise between minimizing AX minus B, which is something that you want to be 0, right? But it's not, because you have too many equations, and no matter what X you choose, you still will have some error. But you want to minimize that error, and this is what least squares is doing, right? But now I'm saying, well, I have too many solutions for that kind of minimization. So I have multiple different solutions which would solve that minimization. And at them, I will have same kind of AX minus B error. Okay, so I might have multiple minimum points for that minimization. So it's not enough. I need to choose what minimum point will also provide minimal norm of X, which means smallest vector X overall. And the question becomes how I minimize it in such a way that I have some sort of weight to that minimization of X norm squared. Now, you can place this is just parameter of the problem. We don't know what the parameter is. You need to choose some parameter which will work well for your problem, and you have multiple different methods to choose that parameter, which will tell you like how much you want to minimize the error between AX and B and just X, how much you want to minimize them. Now, more you minimize, like closer to 0, you get that alpha coefficient, closer to regularly square you get, right? Because then you completely ignore the X norm squared if alpha equals to 0. That will be regularly least squares for alpha equals to 0. But when alpha goes a little bit larger, you give more and more weight to X to minimize X. X becomes more and more sparse, more and more small. Okay, you minimizing the X. And when alpha becomes huge, you don't care if you will have like big error in least squares, you care only that X will be small, right? This is the intuition behind it, how you optimize things when you minimize that kind of things. So more penalty you give to X, and alpha is practically penalty on having big X. So more penalty you give to X, smaller the X becomes. But then bigger the error becomes for the regular least squares. And this is how you can think about coefficient alpha. And it is continuous coefficient, so you can think about that. So it becomes like from regular least squares, it goes up until it gets to completely no least squares. You're completely ignoring the equations, and you're just trying to make X equals to 0, okay? This is all you care about. Your result will be close to 0. And this is why it's not a great idea to choose alphas which are huge. Right, it just will give you X close to 0, which is maybe not very interesting, not relevant for your equations. All right, so here's a solution for that least square problem, which is modified least square problem, ridge regression. The only difference that you see here is that you're adding on the main diagonal of matrix A transpose A, value is alpha squared. And alpha squared is obviously, alpha is positive number, okay? So you're adding to each element on the main diagonal of A transpose A before you're doing regular least squares. You're adding alpha square to each value. So you're making main diagonal much stronger, much higher. What does it do to the matrix and eigenvalues of the matrix? It shifts them. When you add in some constant to main diagonal of matrix A, any matrix, it shifts eigenvalues by the same value, right? So practically it is shifting eigenvalues of A transpose A, and you don't want eigenvalues of that matrix to be zero. So when you're shifting them from zero, okay? You're adding some number to them, so you're shifting them from zero, and the matrix will become invertible. Farther away you get, more invertible it becomes. Okay? It's like you don't have any eigenvalues anymore. And in that case, they are practically singular values, if you remember, right? Because eigenvalues of A transpose A are singular values of matrix A. This what the thing is. Okay, so the singular values, because this matrix is transpose of this matrix is the matrix itself, so it's symmetrical matrix, which means that all of the eigenvectors, eigenvalues are real, and in that case also positive or zero. And this is why singular values are just positive or zero. So in that case, you're just shifting them with something positive, so you're making them even more positive, right? Shifting them from zero. And this is the overall idea that this matrix will become stable. This will become always invertible for alpha large enough, all right? And then you can compute that type of formula, and you will have solution which is minimizing the weighted sum between least square solution and minimizing x. All right, this is the overall idea of Tikhonov regularization. Any questions on that? Yes.
Can you explain the intuition behind it again? Because so for this minimization, we are trying to just minimize the distance between the real B and then AX. Right? So why, are we adding kind of the intuition is still not clear to me.
Intuition. Okay, I will show maybe a little bit of intuition in a second, which is, it's, again, I don't know how easily to connect it without using a lot of math, but I will tell you the connection. I will tell you the connection without proving it, okay? So just before that, I have another thing for underdetermined systems where you have less equations and variables. You can do the same thing, but formula looks a little bit different. Again, you can solve that as optimization problem and you get analytical solution, which is very nice. But here is intuition behind it. Practically, you can think about that regularization as smoothing filter. So what we've done before is made the rank of the matrices lower than its original rank by zeroing all of the singular values which are close enough to zero, okay? So this is what we've done to remove some sort of noise. So Tikhonov regularization is very similar process. We're kind of getting rid of smaller singular values, but in smooth way. You're not cutting it by particular threshold, saying like up to rank K, I will keep all of them, and after K rank, I will remove them and make them zero. So Tikhonov regularization is practically modifying them in a smooth way, like you have that curve here. Okay, so this is dotted line, right? And this dotted line shows you truncation using SVD. Okay, this is what you do. You practically pick in some particular size for sigma. Okay, and by that sigma, everything below that sigma, you're making it zero. Everything above it, you're making it as is. You're keeping it as is. Okay, so this is kind of filter that you are using step response almost at particular chosen threshold. So Tikhonov regularization is doing similar thing, but it's just multiplying that by that kind of curve. Okay, so it is making your smaller sigma values even smaller and keeping all of the big ones as they are. And in the middle, it gets something in between. So it's modifying all of them, but on a sigmoid function kind of thing. Okay, that kind of function. So the intuition behind that is that you are smoothing your threshold between noise and not noise. And this makes computations more stable because this curve is differentiable clearly. And you can do computations much nicer and they converge better when you're doing that kind of thing. So numerically, this algorithm becomes much more stable. All right. Again, I'm not proving it. I'm just waving my hands and trying kind of to give some hint on where things are coming from. But proof is a little bit complicated. All right. So I'm not getting into that. Any other questions? Yes.
Question. While I see the bottom right, there's a 2 over there. AX minus B, the norm
It's a Euclidean norm squared.
norm
So second norm is like L2 norm. L2 is Euclidean norm is square root of sum of squares. So this norm is called 2. One norm, if you remember, is absolute values, sum of absolute values, which is like city block type of norm. You have Euclidean norm, which is 2 norm. And you have P norm, which is Minkowski norm, generalization of all of them. So it will be root of P's order for sum of P's degrees of variables. Okay. And it also generalizes maximum norm, supremum norm, where P goes to infinity. Then you get maximum of all of these absolute values. That's also norm. All of them are Minkowski norms. So this 2 that you have on the norm at the bottom, it's name of the norm, which is Euclidean. And square is the top 2. Okay? Is it clear what I'm saying? So the bottom 2 is just name of the norm, what norm you are using here, which is Euclidean, and upper 2 is the square. Okay?
So this is actually the norm of x squared, but it's a Euclidean norm.
Euclidean norm of x, yes. So this is, that solution is particular for the Euclidean norm squared. All right? You can find solutions for other things, but for norm 1, you don't have any analytical solution, so it's like you don't have formula for it. You can optimize on it, right? You can find solution using some iterations and algorithms, but you don't have closed formula. And this is the beauty of this, some of these approaches, that you have closed formula for it. You don't need to iterate on anything. Just put numbers in the A, compute that formula, and you're done. You get the solution, analytical solution, which is very nice to have, very rare in computational linear algebra. Here's one way to compute optimal alpha parameter, which is practically, there are multiple ways that you can do that, but this is computationally relatively easy way to do that. So optimal alpha, in a sense of leave one out cross-validation, which was developed by these 3 mathematicians. And you have just simple formula that you put numbers in the formula, you optimize it on the alpha parameter, which is minimizing that kind of formula. And formula at the top and at the bottom are practically the same. Just at the bottom you're computing trace, at the top you're computing norm squared, at the bottom trace squared. And that ratio of these 2 things will give you optimal parameter, which means that if you're pulling one of the variables out, you will get it cross-validation minimized, okay? Best cross-validation that you could get using that particular alpha parameter. Is it great for all applications? No, not really. But this is analytical way of finding things. And you have many more. Typically, just experimental, you're playing with different alpha parameters until you get something which is reasonable, works well, that kind of thing. But this gives you some sort of formula. And by the way, the first author on that paper, Golub, he's a very famous person in linear algebra space. He was one of the developers of many of these decompositions and other least squares problems. And I showed you his textbook as one of the Bibles for matrix computation. It's called Matrix Computations. It's like that size of a book. It includes everything, and if anyone does any work in numerical linear algebra, they cite that text. Okay, because it has everything in it. It's now, like last edition, I believe, was 4th edition. And like this book is like cited enormous number of times. And he has like probably hundreds, thousands citations for his work. He is one of the top cited scientists in general in computer science. And I believe I looked some time ago, he, as you can see, he passed away in 2007, and he has, even now, like this year, he has more than 5,000 citations per year for his work, okay? He like done for 20 years, okay? Never published in the last 20 years, obviously. He has like more than 5,000 citations per year. Like 5,000 papers cite his work every year. And it's pretty flat, okay? Every year he gets like plus 5,000 citations. All right, interesting person. He worked as professor at Stanford. All right, so we can continue in the same direction and talk about multi-objective least squares. So you can think about Tikhonov regularization as essentially least squares for two systems of equations. One system is ax equals to b, that you want to make it as close as possible. And second system, x equals to 0, which is also linear system of equations, which is like I times x equals vector b, which is 0, right? So this is second system of equations, but very simple system of equations, okay? Degenerate system of equations, x equals to 0. So you are minimizing that with particular weighting factor alpha between them, okay? And alpha tells you how important that thing is. So I want to generalize it to more generic system of equations. So second system of equations will not be x equals to 0, but will be cx equals to d. And this is how you minimize it and how you get actually to the previous formula if you want to, okay? So you are doing stacking these matrices together, and you're stacking these vectors together in a same long, tall matrix, all right? The idea is that the first, this will be block matrix, okay? You'll have two blocks in that matrix and two blocks in that vector. Upper block, lower block, upper block, lower block. So if you're thinking about that, it's ax equals b, which is upper block times entire x equals b. And since the widths of this matrix and widths of this matrix are the same, you actually can do that. So this is the conditions that the dimensions might need to match. Otherwise, you cannot stack these two systems. So both systems need to have exactly the same number of variables, all right? And then second will be alpha cx equals alpha d. So alpha could be canceled. I'm not doing anything with that. So why not to cancel it? Like, why do you even need alpha here? Any guess? Like why I added alpha here and alpha there? If you can cancel it, because I multiply by alpha both sides. So I'm not doing anything with multiplying by any constant. Alpha is just some positive number. Why would I do that? Think about reality, that you don't have that equation equal here. It's not equal. It cannot be equal. You don't have solution to equal. This is why we need least squares in the first place. So what happens here, this is approximately equal to the right side. It's equal to that right side plus some error, which I want to minimize. This is what least squares does, right? So it's that thing plus some e. And I want to minimize square norm of that e. This is what least squares is doing. So what happens is it will be alpha c equals alpha cx equals alpha d plus some error, which you cannot cancel alpha, right? And this alpha will tell you how important that second equation is when you're minimizing that error, because this error, you can divide that by alpha both sides, and error will be divided by alpha, right? And it's positive number. So you're practically scaling the error of bottom part versus the error of upper part when you're minimizing the error, right? So larger the number multiplying the error is, more you're minimizing that part of the error, okay? And smaller the number is multiplying that part of the error, less that part will be minimized. Because if you're minimizing something, you want to minimize all of them equally, in a sense. So if you're doing that, you're already balancing how much effort you need to put to minimize each one of these parts, okay? So the idea is that you add in that alpha coefficient, and this will be your weighting coefficient for your error, all right? And then you're just doing regular least squares on that kind of equation. So you're thinking about that as your matrix A now, this is your matrix B now, and this is AX equals B, just longer one, twice as long maybe, all right? And you're doing regular least squares, you don't care how long it is. Least square works on any kind of matrices, doesn't matter. And you will optimize it based on your constant alpha that you have chosen. And for C equals to I and for D equals to 0, you'll get regular Tikhonov regularization mechanisms that we've seen before. So this is how you handle that. And this is a solution for that multi-objective least squares where you have multiple parameters. And now one of the last things that I want to show on the theoretical part is how you do constraint least squares. And after that, we'll talk about total least squares. So constraint least squares means that you want to minimize error between AX and B, which is regular least squares, but you also want to impose some constraints. And these constraints you cannot break. You cannot have any error in this constraint. So you have additional system of equations, Cx equals D, but this Cx equals D is not approximately equal. It's exactly equal. So all of these equations might fit. And here a simple example where this might be useful. Let's say you want some function going through the points, you fit in that function to a bunch of points, and you want that function to pass through particular points, but not all of them. So you have some knee points, breaking points of some kind, important points. So you want that function to cross exactly through these points, but not through some others. Regarding all of the other points, all you want is that it will be close enough. Which means for these other points, you want least square solution. And for these particular points, key points of some kind, you want exact solution in function fitting, okay? You have that kind of thing in B-splines, splines in general, cubic splines or whatever, where you have some knee points through which you want your function to pass, and then you do an interpolation between the points, and you want it to be close to other things, and so on. So this is the idea. It goes, again, I'm not showing you where this comes from. It comes from Lagrange multipliers, which are called lambda. I don't know if you learned that in any calculus courses or anything like that. Have you heard about Lagrange multipliers? Some of you maybe heard about Lagrange multipliers. It's just minimizing that using Lagrange multipliers. You get optimization criteria, you get some cost function, minimizing that cost function, you get some solution out of it. And the solution, luckily for us, is also analytical, okay? And this is the solution that you see here. You have blocks, 4 blocks now in matrix A instead of 2 blocks of matrix A. So you have like A transpose A in that corner. This is block matrix. This is block matrix C, C transpose, block matrix of 0. It's not necessarily like single number 0, it's block of zeros. And then you have vector X, lambda is coefficient, all right? It's just number, which you also minimize and optimize on it. But later you will ignore it, you don't care about that number, you care about X in that solution. And then you have A transpose B here and D here, okay? So in a way, kind of similar to the previous one, but different. And then you're doing regular least square on that kind of matrices, right? Again, you have form which is AX equals B, different A, different X, and different B, but still same kind of shape. And you're doing regular least squares on that or any other approach that we've seen before. And in MATLAB, it will be simply just 2 lines of code. So you'll have to define that matrix, which is A transpose A, C transpose, and then second will be C and zeros of the size C1, because lambda is only like 1 by 1, so it's like number, right? So this will be all row. So C will be a row vector, and 0 will be row vector of some kind. So dimension should be 1 here. And then you can inverse that times that thing, or you can do like backslash is like inverse multiply in MATLAB. Familiar with that? Backslash function, which is inverting the previous matrix. So this is the operation, okay? Just simplified way to write that. And then you have A transpose B, and you have D in the second vector, all right? And X will be just the first part until the last column. So you ignore the last column, and then you get that X from the solution. Okay, so this is how you compute it in network. Any questions on that? Okay, and now I think the last thing about that lecture before we go to any kind of applications. You want to find something which is called total least squares sometimes. And the idea that we used before is that AX equals approximately B. And if you wanted to make it equals to B plus some sort of error, right? So we thought that Y measurements, which are in vector B, are somehow noisy. We don't know them exactly. These are measurement stuff, right? We measure all kind of Y values, and they might be not exactly right. This is the overall point, right? Now we're thinking maybe also values in matrix A are not exactly accurate. So X's, like inputs, might be also not accurate. And we might have some tolerance of inputs that we are putting into the system to measure these outputs. And the idea is that matrix A also could be uncertain in some ways. And this is the overall idea of total least squares. So the idea is that you have, let's say, matrices A, X, and B, and you want to find smallest change in the matrix A and change in the matrix B, such that this will have that solution of AX equals to B. All right. So you want to minimize the errors of matrix A and minimize the errors of matrix B. Before that, you had only errors of matrix B. Okay. Now you have also here errors. And if you're thinking about that in 2 dimensions, what would minimize the error between your model and your bunch of points? It will be orthogonal projection from these points to this line. Not vertically, not horizontally, but orthogonally to the actual line. Okay, so you're projecting it not vertically, not horizontally, perpendicularly to the line. Okay, this is the shortest distance to that line. And this is exactly what total least squares will provide you, but in n dimensions. It will be actually the shortest distance from your model. So you'll project it in such a way that it will be all orthogonal projection in that sense. And the solution is also analytical, which is very nice. Again, I'm not proving it. This is a solution you do in SVD of stacked matrices. So you're putting together A and B as a single matrix, which will be obviously wider matrix. And then you're doing least square solution using singular values as usual, kind of regular SVD decomposition of that matrix. And this will be the solution. V12, which is these block matrices. Okay, so you multiply this block by inverse of this block and minus of that. Again, I'm not proving why is that. And calculation is again following exact formula here. To do that, you're doing SVD of that stacked matrix together. And then you're taking particular components out of the V matrix. Okay, this will give you a total least square solution for that problem. Okay, any questions? And you have many more. You have weighted least squares. You have all kind of other least squares. Yes.
So why is this? I mean, this appeared to be kind of better than the normal least squares in terms of
Unless your matrix A is accurate.
less.
Matrix A is accurate.
Which means
A
A
might be precise. You might know your inputs.
exactly. If you send particular pools of particular size, you know what the base is. You don't need to have tolerance on that base, right? So you don't need it. And that computation is clearly much more complicated than computation of least squares. Computationally much more expensive. They have many more computations here that you need to do. Your matrices are much bigger than the original matrices. So it's depends on what you need. Okay. Yes, this will be more accurate generally, right? But more computations, computationally more expensive. Any other questions? All right, some simple examples first. We will get back to electrical engineering a little bit, but don't worry, it's not that difficult. All right, so let's say we have some system, we want to estimate input impedance or resistance of that network of something, okay? So how do we do that? We send some current in, measure some voltage on the nodes of input, It could be input or output, it doesn't matter in that sense. I'm using input just as example, all right? And you get some value for voltage. And we know the Ohm's law, which says that resistance is voltage divided by current, okay? And then you can estimate resistor from single measurement. You're sending 1 milliamp, you're getting 1.5 volts. So this is 1.5 kilo ohm resistance, okay? This is what it means. It's 1.5 divided by 1,000, not 1,000, by 1 milliamp, which is 1 divided by 1,000. So it's 1,500 ohm, which is 1.5 kilo ohm, all right? But this might be not accurate. So you need to do multiple measurements. You're measuring that multiple times. And each time you get something different, a little bit. And you're sending different currents, maybe like 1 milliamp, 2 milliamp, 3 milliamp, 4 milliamp. And each time it gets you some values, measurements values. Or you can continue doing like 1 milliamp, and that will give you all kind of same values, but you want to vary it a little bit. So let's say these are the values that you get. So you have two vectors, input vector, which is 1, 2, 3, 4 milliamps, and output vector in volts, which is like that kind of volts, okay? Obviously, this will not give you single possible solution. Why? Because they contradict each other, clearly. The voltages, one time it tells you there's like 1.05, another time it's like 2.01 divided by 2, which is could be similar, but third one is very different. So like some of them matching, some of them not matching at all. So what we need to do is just to formulate it as least squares problem. And I'm using matrix C specifically, vector C specifically, because I don't want to use I. This is for current, right? And like an electrical engineer, we always use letter I, but in linear algebra, we use I for something else. So I don't want to mislead you with names and to write I times R equals V, which is Ohm's law, but here it's like C times R equals V is just law by Ohm, right? So practically speaking, vector that you have here, which is currents times resistances, which are unknowns, okay, equals to V. So it's like A times X equals B. Linear relation between them somehow, okay? Just apply least squares to these three matrices. So your A equals to C and your B equals to V. That's it. So you just put in C transpose C, inverse C transpose V, regular least square solution, and you will get best estimate for your R input. Okay, so far, relatively simple. Let's try something more complicated. And you have some MATLAB code, which is just computing that, and you get the correct result for that. How about estimation transfer functions, control systems, that kind of thing? You have transfer functions with some parameters, all right? So these parameters will be, let's say, B2, B1, B0, A2, A1, and so on. Okay, so you have multiple parameters that you want to find. In that case, you have 5 parameters, right? And this is your transfer function in discrete filter, let's say. Okay, so you want to design discrete filter. You have, or not to design, you want to identify transfer function from given input-output relation. So you send some input, you measure some output, you have all of these corresponding points in time, okay? Samples in time, input samples, output samples. You want to estimate what is your transfer function, which is generating these output samples. And sometimes you have the samples also noisy, obviously, because you're measuring this particular tolerance, so they are not exactly coming from the transfer function, but from output of transfer function plus some sort of noise. Right? This is typical situation where you want to identify the system identification type of problem. So I can write that transfer function as difference equation, which is each multiplication by z is practically delayed by one sample. Okay, it's like -1 each time you multiply it by z. So since you have like power 2 here, then it will be shifted by 2. You don't have to remember any of it. I'm just telling you that this is completely equivalent difference equation to the transfer function. Like if you learn signals and systems, at some point of your time, you saw it before, okay, how you convert from transfer function using inverse Z transform to regular difference equation, okay? If you never took that course, that's fine. Believe me, this is the result, okay? That's fine. This is a difference equation, and you start with some initial conditions. So start with some initial point where you have yk minus 1 and k minus 2 are given to you, and k minus 1 and k minus 2 given to you as numbers, your initial conditions, and then you start to iterate from this initial condition somehow. Okay? Typically assume that u before 0 is 0, so you don't need any of these things, and somebody gives you these two initial conditions on y, like what was, like where y started from. That's your initial conditions of your system, of your filter, okay? So we're measuring, given some input u of k, so these are samples that you send to your filter as input, we'll call it u of k, and the output voltage is what you measure, we call it y of k, okay? So these are samples of the output voltage over time, and what you want to estimate are these parameters, a1, a2, b0, b1, b2. This is what we want to find, actually, from these measurements, input-output relations. So you're thinking about that, like you have some black box, you poking it with some voltages, you record some output, some responses. You want to know what is that black box, assuming that you know approximately the model, which would be the second-order model of some kind. Okay, this is your assumption of the degree of the model. And we'll also assume that some measurements are noisy, so you do not measure them exactly, precisely. And that's a typical problem in any estimation problems. And we want to estimation error to be minimal in that case. So we want to minimize the estimation error. And this clearly will be overdetermined system because you have tons of points and only 5 parameters to estimate. So more points you have, more reliable your estimation will become, because the error will be based not on noise, but on the actual system parameters. Okay, more data points you have. So the matrix A will be kind of long and thin, a lot of equations. Okay, so let's rewrite that in terms of least squares. So in least squares, we want to rewrite the problem in such a way that there will be some sort of matrix multiplied by list of unknown parameters, which is vector. Okay, so on the right, from that matrix, we'll have practically all of the A coefficients and B coefficients. And then we will have measurement vector of some kind on the right. Okay, this is how we want it to look like, in a sense, right? All of the least squares problems, we need to bring it to that specific form AX equals to B, kind of thing. So here's how it goes. So we know this is the same equation that I showed on the previous slide, yk equals some function of previous y's and previous u and present u, all of that stuff. And in that case, all of these things, which are y values, are numbers. These are measured outputs of your system, okay? All of the u values are inputs that you give to the system. So they are also numbers. And B1, B0, A2, all of these are unknowns that you want to find, to figure out, okay? So let's organize all of the knowns into the matrix and vector, and unknowns into a separate vector. And I want dot product between first row of the matrix A and matrix X, right? This will be the first element in the matrix B. So here's how it goes. So matrix B will be all of the values of UK for k equals 3, 4, 5, 6, whatever number of points you have, okay? So I'm starting already from 3 because I don't have like 1 minus 2. I don't have any values for that. So I want to start already with some known values. I will skip the first 2 points. Okay, I will ignore the first 2 points in your measurement. I will start with point 3 that I will have already point of y1. Okay, and I will start with y3 minus 2, which is y1, which is already measured. Right, I don't know initial conditions, and I don't care, because I can measure the first point. All right, so I will start with 3, and we'll go point by point, 3, 4, and here's what will happen for each point. I can write that same equation as minus yk minus 1, which is that thing together with that minus sign, multiplied by a1, plus minus yk minus 2, together with that minus, which is the second element in that vector, times a2, which is that coefficient, plus, here you have b0 times uk, so third one will be uk, and then uk minus 1, uk minus 2, this will be my vector, times vector of unknowns. So right now it's like vector by vector, but I can do that for every k. and I can stack them together, one below another. So what I will have here is something like that. So I will start with k equals to 3. So it will be 3 minus 1, 3 minus 2, 3, 3 minus 1, 3 minus 2, and so on. So this will be that first row. Negative y2, negative y1, u3, u2, u1, times all of that vector, that transpose, okay? And this will be u3, because k equals to 3 at that point, right? So I start with k equals to 3 first line, k equals 4 second line, k equals 5 third line, and so on, whatever number of k's I have, whatever number of points I measured, right? So we have very long matrix, and all of these things are numbers, right? Because you know what your u at particular sample, and you know what your y, which is measured value at that sample, okay? So these are all numbers, and these are all numbers, and these are variables that I want to find. Again, you have ax equals y's kind of system, do least square on that matrix and that vector. Yes.
Why k starts from 3? Is because it's an LTI system?
Yes. So this is LTI system, like any system which has transfer functions, LTI system in that sense. So it's, yeah, it is LTI system. So you can shift it in time and it will be exactly the same system. You can start with any time and you can call it 0. Like any time could be called 0. So I will start with time 3 and that's fine, okay? But in that case, it would work not only with LTI systems. That thing would work even with time variant systems, because I can start with any point and start in that matrix from any point. And then the problem will be that I cannot write that as linear combination of things. And this is why least squares, you will need some nonlinear least squares. And you have nonlinear least squares as well. But linear least squares will not work for non-LTI systems. All right? For LTI systems, you can do that. Everything is linear combination of things. And all filters are practically giving you linear combination of all previous points in your signals. So it's great match. Okay, this is why we love linear systems in general. In control systems and signals and systems courses, we learn almost exclusively about linear time invariant systems. Because this is easy, not because this is super useful. But they're close enough to many practical systems, so it's fine. All right. Any other questions?
You said Y's are our outputs and
Yes.
X's are our inputs.
Right.
So why are they not same number of measurements? Like we have 3 inputs, 2 outputs.
It's not 2 outputs. These are samples which were before, recorded before. So system dependent not only on present value of your input, but also on previous values of the input and previous values of your output. So it's like feedback loop, right? You have closed system where present value of your y dependent on previous values of your y and previous values of your input. So they are kind of interconnected on the past. And higher the order of the system, more memory it has and more samples back it can store, and base the present y will be based on all of the previous history of things, okay? So this is like how far in back in history you go. This is all of these delays. This is delay practically in the system.
So we can have a longer equation in this.
So with more delays, you'll have longer equation and higher order transfer function, yes. The transfer function order is how many samples you store in your memory and compute on all of them. Okay, so it's dependent on all of the past. All right, any other questions? Okay, so you're just estimating that using least squares and you get your optimal parameters. And here's MATLAB example for that. A little bit difficult to see maybe on smaller screens, but you have some gray line here, which is the original response to white noise of your particular system. And your particular system is given here. So this is coefficients of A, coefficients of B, the real ones, okay, the original filter that you have. And you filter in white noise, you get that kind of responses. And these responses are that gray line below the red dashed line, okay? And as you can see, I reconstructed that with coefficients using that least square. And I reconstructed that signal, and this is that red line. And it replicates pretty fine the original one, okay? They're almost the same. You have a few kind of places where they're not exactly the same, but most of the places they are completely fine. Okay, and this is for clearly noisy signals, it's just white noise. And here is how it goes. So you have A and B vectors. These are kind of A1, A2, and then B2, B1, B0, I think. No, the other way around. So this is like coefficient of the highest degree, middle degree, and free coefficient. Okay? Don't remember how I define that in the transfer function. Yeah, so B0 is the last one, practically. So 0, 1 is B0, B1, B2. Okay? Depends on the order in the transfer function. So what you have here, you have number of samples. So I measured 200 points, 200 samples in my input-output relations. And you can choose any number of points you want. This is just simulated data, so it doesn't matter. I just picked 200 points. All right, you have input signal, which is just white noise. Rand n in MATLAB gives you random values out of Gaussian distribution, normal distribution, all kind of numbers, positive or negative. And you can see that they look pretty random, okay, jumping up and down all the time. And they're also independent of each other. So each value that you get in that vector is completely independent from all other vectors, all other values in the vector. So it's IID signal. Now I'm simulating that signal. So I'm computing like what that system would be doing using that equations that we had before, okay? So I'm taking the first value of A times yk minus 1 minus second value of k times k minus 2, and so on. I'm just writing that equation and simulating to generate that gray graph, okay? The original filter graph with true values of A and B, because I know them, okay? Because I generated them in the first place. In reality, you don't know them, so you cannot use them for estimation, obviously. You want to find them, okay? So what happens here, I'm adding also that random noise to the measurements. So measurements are imprecise, and you get some sort of tolerance on that. So it's noisy measurements in some particular sigma here. So y will be equal y plus that noise. Now, I want to build that regression matrix. I'm building that regular least squares matrix as we had before. So I have all of these values of matrix A starts with nothing. So this thing is practically nothing for k equals 3. And then I'm building that matrix, okay? So this matrix will look something like that. So you have minus y k minus 1 minus y k minus 2. So just pay attention that this is the same thing. I'm just copying that same thing, okay, that line. But this will be for each k, so I'm doing that in for loop. So I'm adding more and more lines like that, all right? And your vector y will be all of the measurements starting from k equals to 3, because I'm starting at k equals 3 everywhere. And this will be that measurement vector y that I just generated here with noise. So this value will be pretty noisy, okay? I don't know exact values of the measurement. They have some tolerance. Now, my estimation will be regular least square formula, okay? Recognize that now, by now, hopefully. A transpose A inverse times A transpose times B. Okay, this is my estimation. So these are estimated values. And pay attention, these are true coefficients that I have. I'm just copying them from here. And these are estimated coefficients. They are not exactly the same because of the noise, but they are close enough, right? Like you get about like 0.69 instead of 0.7. You get 0.21 instead of 0.2. They're close, okay? They're not perfect, but they're close. And then when you reconstruct it back in terms of least square error, you get minimal least square error. Okay, so this is the best you could get given noise and given practical limitations that you have here. And then all I'm doing, I'm practically displaying these coefficients, which is what you see here, okay? Now, for different noise, you might get a little bit different values here, but they're all still close. Each time you generate new noise, it might look a little bit different, obviously, okay? And then you compare the results. So practically, I'm copying that thing from here But instead of using true values, I'm using estimated values. And this is what this kind of dashed line is, okay? Using estimated values instead of regular values, real values. And as you can see, it works pretty nicely for these squares. All right, any questions on that? Okay, so we'll have someone working on image deblurring, so I will just skip fast through that kind of thing. And I don't have much to say about that, but image deblurring could work the same way as regularly squares are working. So here's just one brief example on how you can do image deblurring. And we add in some Gaussian noise to some given image, you get something blurry like that. And then you can reconstruct it with ordinary squares or pseudo-inverse or with some Tikhonov regularizations on some other stuff. And the MATLAB code which will do that is also pretty basic. So we'll skip through that thing. Now we have sensor calibration where you have demo on total least squares where not only your measurements are imprecise, but also your inputs that you put could be imprecise. And again, there is nothing secret here. It's same things that I'm talking about already for more than an hour. And the idea is that you just writing that as AX approximately equal to B. And you know that A values of your inputs might be kind of plus minus something tolerance. And B measurements are also noisy. And then all you need to do, you just doing total least squares on that and you get the solution. And this could be any kind of sensor. It could be any kind of measurement. It could be from neuroengineering, you can use like EEG calibration or acceleration calibration or optical sensor. It could be anything. Okay, so it's useful for any kind of measurements that you're doing on noisy data. All right, and it gives you best solution in terms of least squares of error between your model and whatever you're trying to get from the data. All right. So you just stacking the A and B, you're solving that thing using sigma, and then you computing that, and you have basic code which is doing that. Okay, as example. So you have noisy A, noisy B, you have true values and noisy values, and then you're stacking them together, finding the result. So true parameters was like 0.5 and minus 0.3, and total least squares estimate will be 0.5 almost, and negative 0.29 instead of 0.3. So it's close enough, okay, as expected. Just for you to show that you can use MATLAB code to do that in a few lines of code. This one is what we want to focus on as the last part. And I want to show, and I will also go fast through that because I assume that not many of you are interested specifically in computer vision or anything like that, but this is just a good example of how things could be transformed into least squares, where seemingly they are not exactly least squares, okay, have nothing to do with that. Just interesting example. So we will start with affine transforms, and affine transforms are very popular in computer vision. This is kind of rigid, mostly rigid transform, where you can rotate the image, scale the image, share the image, things of that kind, scaling of different kinds on different dimensions. And it is approximately working with planar images, orthographic cameras, kind of regular stuff, basic stuff from computer vision. So it's relatively simple, and it could initiate, typically we are doing registration between objects which also could deform somehow non-linearly. Okay, so you have some sort of deformations in objects and you want to match, let's say, as example, you have CT image of lungs and we have inspiration and expiration image of lungs. These are clearly two different time points where patient went through inspiration versus expiration, and you want to match one with another to do all kind of comparison of measurements. What happened when they expire the air out and when they inspire the air in, all right? So you want to match these two volumes of lungs point by point somehow, which is very difficult problem to solve and unsolved problem. You can approximate it, you can get some results. Not all of them are great. You need to correct by hand a lot. You have issues with that, even with modern deep learning and all of the other approaches that we are using. it's still not very reliable. But the first step is always how you align overall picture with overall picture to center one image on top of another image, to allocate them in the same place. So you need some sort of translation, rotation, because patient might be kind of lying down in different angles a little bit. The machine is oriented a little bit differently. You have some angle, body is not always in the same position, especially at two different time points, right? They're breathing in and out, so their body is moving when they are in the CT machine. So all kinds of things are happening. We need to align them somehow. This is big problem, registration problem in computer vision that we need to solve. So first step is doing that rigid registration, like how much we need to move the image and rotate the image and scale the image that it will fit each other. Close enough. Not perfect, but close enough, okay? And only then you do non-rigid deformation registration between the two volumes. So this is that first step to initialize different things. And how it could work. Here is one example. Using feature points. So you're finding all kinds of key points like corners, blobs, small blobs of some kind, which are reliably detectable in both images. And you find relations, which are called features, okay? This point is called features. And you find relation where this feature went in the second image, okay? And you will have that line connecting one image to another image. And you want more of that kind of points. So you'll have kind of fitting between pairs of points. And you have n pairs fitted. Some of them will be reliable, some of them will be outliers. Obviously, you will get features which are incorrectly matched between the two images. Not all of them will be perfectly matched, like in the toy image, all right? So you'll have some errors as well. But generally, you will have coordinates xy from here goes to coordinate xy here. Okay, so you have pair xy, xy matched. Another pair xy, xy matched. And the transforms, which we are looking for, written that way. This is affine transform. You have 6 parameters to that transform. This is multiplication by some sort of matrix. So each new coordinate in that image will be affine transform of the original coordinate in that image. It's multiplication by matrix M, which is like all of these parameters that you have here, plus translation. So it will be shifted by T1, T2, T1 in x-axis, T2 in y-axis. And also, if you remember, we had rotation matrix here. So if it is like cosine, cosine, minus sine, and sine, then it will be just pure rotation with angle theta of some kind. But you can also add scale here. So you can multiply that one by constant and that one by constant, and it will scale in that direction, and it will scale in that direction differently potentially. Okay, you'll have main diagonal multiplied by S1 and S2, which would give you scale. You can do all kind of other stuff with affine transforms. But this is generic description of affine transform and doesn't look like AX plus B, all right? Not at all. But what I'm saying, you can convert it into AX plus B. This is how you do that. So you want some matrix A times list of parameters. And my list of parameters are all of the M, and 1, 2, 3, 4 from the matrix M, and translation parameters, which are T1 and T2. So I'm writing them immediately in that vector here, okay? Now I want to replicate exactly the same equations between inputs and measured outputs. So my inputs are encoded by xi and yi somehow, which are coordinates of that matched point. And outputs are x prime and y prime points, okay, in the second image. These are numbers that I know. These are numbers that I measured. I have these coordinates, okay, they are numerical. These are numbers. So I want to write something in the matrix A times z vector equals z vector of measurements with primes. So let's say, what is xi prime? So if you're looking on that equation, first equation here, xi prime equals m1 times xi plus m2 times yi plus t1, right? This is my first equation in that affine transform. So I'm trying to replicate exactly the same thing with that first line. So it's xi, which is that line, equals xi times m1 plus yi times m2, right? The second one, plus something times m3, which would be obviously 0 times m3 because I don't have any m3 in that equation, and 0 times m4, plus T1 times 1 plus 0 times T2 because I don't have any T2 in that equation, okay? So I'm replacing just with zeros all of the missing parts, practically speaking. And same thing I'm doing with yi, okay? So I'm writing that kind of equation. I have no xi and yi in that equation at all at that first place multiplying m1 and m2 because second line here has no m1 and m2, right? So I'm just putting zeros here and shifting it here. And then I'm adding T2 instead of adding T1 and multiplying by 0 T1. And I get exactly the second equation here, all right? So this is how I convert it into some matrix times some vector equals some vector, which is AX equals to B form. This is the form that I wanted in the first place for least squares, right? Now I can repeat that same operation for each matched point. And I will have pair of lines for each matched point. Okay, 2 more lines and 2 more lines and 2 more lines for each pair. I will get that pair of lines. So this matrix again will be very long if you have a lot of matched points. You do least squares on that, and you get best set of parameters M and T. This is how it works, all right? Any questions on that? So last thing that I wanted to talk about is related to what you do with outliers, because one outlier might do a lot of trouble to you. So for example, if you matched some point which was incorrectly matched like that, like window to window, but different window, right? It's not the same point, not the same place. And if you match them, you'll get clearly incorrect match and you'll have outlier point. So if you have some outlier, linear regression works horribly. Okay, believe me, least squares is not doing good job if you have some big outliers. Let's say here a simple example. If you want straight line passing through all of these red points, it will be great. But if you have even single outlier like that, this is how your solution will look like, okay? Not even close to the real line with single outlier. And this is actual regression line for that type of example, okay? Because you have one outlier which is far away, it generates a lot of error squared, right? Because you're minimizing squared error. So the single point will generate square, which is huge, because you're taking error and squaring that error. And since this error is huge for the original line, if you're taking that original model, the distance will be huge. You squaring the distance, you get horrible error. So this is how will linear regression look like for that set of points. Single outlier killed it, practically not very useful. So here's the solution, which is genius solution, actually. It was from 81. I guess no one here except me was born at that time, long time ago. But the idea is so universal and so useful for just removing outliers that you can use it not only in regression problems, you can use it practically anywhere. Ideal solution for everything when you want to fit some model to any bunch of points with outliers. And you can have multiple outliers, like 50% of them. Who cares? Doesn't matter. We just need to do more iterations on that. And here's the idea of Ransack algorithm, random sample consensus algorithm, okay? So here's how you do that. You try to avoid all of these outliers by using only inliers, but this is chicken and egg problem. How do you know that some point is outlier or inlier, okay? You have no idea, right? There is no criteria which will tell you like what is inlier and what is outlier. If you would know, you would throw them immediately, right? You don't, typically in normal conditions. So what happens is you pick some random fit, okay? Let's say you have a bunch of points, you want to fit straight line to it. You pick 2 random points, whatever they are, they could be inlier, outlier, who cares? You fit the line to these 2 points, pass that line through these points, and you're measuring square error to this line, okay? If this is inlier points, your square error will be smaller compared to if one of these points or 2 of these points are outliers, right? Because if you picked the wrong point and you passed line through that point, and 2 points define line, right? So you can pass line through these points, you will not have that many inliers to that particular line. So this is exactly the idea. Try a few configurations of pairs of points and pick the one which has most of the inliers, which means that the points that you have chosen are inliers, most likely, okay? Now, when you know that they are inliers, take only points within some boundary around that thing and compute least squares only on inliers, okay? Which will correct that line a little bit to match most of the points, okay? Most of the inlier points. And it will completely ignore all of the other points, all right? So this is the idea. I will show you a little bit more probably next time. It will take 5 minutes to complete it, but any questions on the idea? And a very simple idea, but it works. Most surprising thing is that idea that you don't need too many of the random tries. You need only a few and you get like 95% confidence interval out of that. Trying only a few times, you get 95% accuracy, which is surprising, extremely surprising. But you have math behind it. All right. Thank you. So I will jump back a little bit to the previous lecture that we haven't completed on the image transformations. If you remember, we talked about affine transform, where you have rotation, scaling, squeezing, all kind of things, shearing, and you are trying to find the transform based on matching of pairs of points. So you have pairs of features, you're matching the coordinates of these features. You're saying, I will approximate it with some sort of affine transform, which is function rotation and scaling. And then I will find the transform using least squares. And this was the approach. And then we got to the place where single outlier point can make your computation very unreliable, which means when you're using least squares, obviously you are exaggerating the effect of outliers because you are squaring the error. So if one point is just noise and this point is not matched correctly and it has big distance from the reality, okay, it will affect significantly your modeling. And the problem is that single outlier can give you that kind of regression line, right, which is not great, right? It's not what you would expect from that kind of bunch of points. So your model needs to be fitted in much better way, and for that you need some sort of robust fit. And you have multiple ways to do robust fit, but this idea of RANSAC, random sample consensus, which was proposed many, many years ago, I like it in particular because this approach is practically universal. The idea is universal. Idea is relatively simple, and it is universal. You can apply that to any model. It doesn't have to be straight line. It can be any other model. It could be something nonlinear, any kind of function, any kind of even idea that you can detect outliers. So this is called universal outlier detector based on the model. And model could be any model, n-dimensional model, whatever you want, okay? It's just some models that you want to fit to some data. It will work with anything. And I'm showing only simplest examples with how you fit like straight lines, but you can expand it actually to any kind of model, all right? And the idea is also very prominent because it seems originally, like when you initially learn about that idea, it seems to be impossible and surprising actually that you don't need that many random samplings to get the inliers correctly, all of them. But when you think about that, here is the overall picture, okay, big picture here. Let's say you have a bunch of points, okay? And you assume that most of them are inliers. Not all of them, some of them are outliers, maybe far, far away, here. But you would assume that probably more than 50% majority are inliers. So what is the chance that if you pick two random points, they will be both inliers? This is the question that you're actually asking. If your number of outliers is not horribly big, not really close to 50%, like every second point is an outlier, then actually it's much more likely that you will get 2 points inliers, right? And then when you get those 2 inliers, you put in some lines through them or some models through these points, and so on. Then you are finding all of the inliers based on your model, temporary model. And then you can correct with all of the inliers using least squares or any other approach. So the idea is not that crazy. It's not that unexpected that you have not too many times to try these pairs of points or triples of points or whatever your model is, to get all of them inliers, right? And if you get one time all of them inliers, you practically can identify all of the inliers and you can filter out all of the outliers. So you practically can get rid of them. This is overall idea, and this simple idea, right? And computation is not very expensive. So it's relatively easy algorithm and people are using that for all kinds of things. So it tells that you have all of the steps where you're taking 2 points, putting some lines through them. They could be inliers, outliers, you don't know that yet. And then you are building some sort of confidence interval around them. And then you're saying everything in the confidence interval is inlier, which in that case is obviously not true. Okay. So in that case, you're just counting the number of inliers, whatever fits your boundary intervals. And boundary intervals is the only parameter of the problem that you can play with, like how much tolerance you give to inliers, like how close they need to be to your model. So this is a parameter that you choose practically. So you're just counting. In that case, you have 1, 2, 3, 4, probably 4 black points and 2 blue points. So it's 6 points inside that confidence interval. So the number is practically 6 inliers. So you're ranking that by number of inliers. Then you're picking another thing. Let's say you're picking these 2 points randomly. Right, so this is much closer to 2 inliers. So for these 2 inliers, you continue with the same width of the confidence interval. And here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is bigger number of inliers. So you're repeating that multiple times, and you're picking the one with the biggest number of inliers. You're picking the pair of points for which you have the biggest one. And you don't even need to store the ones which are smaller. So you're just keeping the biggest one all the time. You're randomly sampling pairs of points and keeping the biggest number of inliers pair. All right. After you have chosen that pair, practically you're taking all of these points inside between these 2 bars and doing least squares on them. Okay, to get even more precise model. Okay, so this model will not be based only on these 2 points anymore. It will be based on this 11 points. And you will ignore that point, that point, that point, this point. Okay, so this will be your 4 outliers out of this all points. Right, so far, this is general idea of forensic algorithm. We're just trying to fit different kind of functions to a bunch of points. Now, the question becomes like how many times you need to randomly sample that. Okay, and here again, very surprisingly, we have analytical formula to compute that. So let's say your model requires S points to build model uniquely. In the case of single line, straight line is just 2 points, right? So S will be 2. You need only 2 points. For parabola, you will need 3 points, and so on. Like for higher order polynomial, you will need more points to fit them exactly passing through these points, and you'll learn later how you pass all kinds of polynomials and functions through points instead of going with least squares. But in that case, it's just 2 points because 2 points identify uniquely straight line passing through these 2 points. Okay, so far, so we will call that S. So we want to assure probability of hitting the inliers, and we will call it P, and P will go typically like 0.99. We want almost surely to hit with very high probability, you want to hit the pair of inliers at least once out of our N sampling procedures. Okay, so this N practically will be that formula that you can compute, and epsilon will be probability that we have outlier, which means it's kind of you estimating percentage of outliers. You're saying be 20% of outliers, 10% outliers. And if you know all of these numbers or you estimate them well, you can compute what's that number of trials that you need to do until you get at least one of them, both points will be inliers. Okay. And interestingly, these numbers are not huge. These are the actual, this is tabulated function. So this is that same function tabulated for S So in our case of straight line, it will be the first row, okay? And this is proportion of outliers, 5%, 10%, 20%. So even if you have like half of your data outliers, okay? Half of it is outliers. And you need to fit only 2 points, which means it's linear regression problem, okay? You want to solve linear regression problem, but robust linear regression now, okay? You want to ignore all of the outliers. You want regression only on inliers. All you need to do is 17 times to try it, okay? But if you have only like 20% of outliers, then you need only 5 random samples, which is not much, okay? It's like computation is super not expensive. It's really simple, okay? And to me, at least this table is surprising because even if your model is like 8 scores, or you have like 8 parameters to tune, you need 8 points to define your model, okay? Which is a lot. The total number of tries for like 40% of outliers, which is like almost half of your data are outliers, a lot of noise, okay? Tons of noise. You need like 200 times to try it, to identify like 8 parameters. It's not much. For any kind of robust optimization techniques, it's like really nothing. Computationally not expensive at all. While other techniques of robust fit, for example, could be very expensive and you need tons of iterations, thousands of iterations until it converges to anything more or less robust until you identify all kinds of outliers. So this is great property of the Transac random consensus algorithm, which is, first of all, universal. So you can use any kind of modeling, use any kind of number of parameters, which will be defined by number of points that you need to fit for a model. And you don't need that many random samples, really, okay? So here is that example that we were using specifically. So n, for example, equals to 12 points, the total number of dots here in that plot. Sample size that you need to build your model is just 2 points, which is straight line. 2 outliers, which is that's 2 points. And again, this typically will be just your guess. So you will not know that number, but here it's obvious that you have like 2 points which are very far away from desired line, which is here. So it's approximately 17%. If you go to the table, it will be kind of close to that thing. So n will be 5. It will be here. 17 is close to 20. So you approximate it with that number. And this will give you 99% of chance that you're getting your inlier pair, which like pair of this point somewhere, okay, inside. And then this is compared to overall number of possible pairs that you actually need to check, which would be 66. Do you know why 66? How do you compare the overall? Like you have 12 points, right? What is the number of pairs of these points where order doesn't matter? This is combinatorics question. Do you understand the question? You have 12 points, which are all practically the same. They are not numbered points. So it doesn't matter if you're taking point 1 and 2 or 2 and 1. The order doesn't matter when you put in line through them. Okay, so you need like what is the total number of possible pairs of given 12 different points?
Of combination too.
So it's combination. How do you compute that combination? You have multiple ways of doing that.
Yes.
7 question quotation mark.
Huge. This will be huge. You're saying like multiply 1 by 2 by 3 by 4, but no. The answer is 66. Like how do you get to that number? So look, you have like 12 points. So you get 1, 2, 1, 3, 1, 4, 1, 5 until you get to 12. So have 11. Then you get from 2 to 3, 2 to 4, 2 to, and so on. So you get 10. And then 9, and so on until you get to 1. So practically you need to add numbers from 1 to 11. This is the progression, the sum of arithmetic progression formula. But you also can compute that as 12 times 11 divided by 2. It would again give you the same thing. This is the sum of arithmetic progression. So practically you just can count them in the simple case and you will get total number will be 66. All right. This is sum of numbers from 1 to 11. All right? So instead of 66, you actually need only 5, which is order of magnitude smaller than overall number of possible pairs. You don't need to check all of them for that algorithm. Any questions? All right.